the matrices AB0D, and where these ABD are all coming from, let's say, rational numbers. Okay? So how do you view this as a vector space? First, you have to make sense out of adding these two matrices, right? Adding two matrices makes sense? Let me go ahead and give you one element in there. 1, 2, 3. Does it look like an element in there? Right. How about 2, 3, 4? Does it look like an element in there? So if I use this natural notation plus, does that mean something to you? How do you add these two matrices? Just each entry in that exact location. Is that 3? What is it? 5, 7, 0 in there, right? That's the matrix addition. Do you know what that means? Why do we even do this? So what was my new view to the matrix? Matrix can be viewed as not the coefficient of an equation, but function, right? This is viewed as some sort of transformation from where to where? Column vector to the column vector, right? Collection of functions. And then there must be some sort of property that listed there so that, exactly given by this particular matrix and so that. So does it look like a space of functions? Yeah, space of functions, right? How about matrix multiplication? It is not part of it. We only do the scalar multiplication, right? So for example, pi is multiplied to 1, 2, 3. Does that make sense so that we can view this as a scalar multiplication defined? Pi is multiplied everywhere, right? 3 pi. And everything makes sense. That's why it's... But you know how to multiply matrix by matrix, right? And you know how to do that. Do you know the meaning of that in terms of functions here? You're multiplying two matrices. If you look at the matrices, each of the matrices representing the function. Right? So let me write down here. M and N are two matrices of the same size. They represent function T1. This represents function T2. All right? No problem. You understand this? Next thing is that I'd like to multiply Mn. Right? You can do that, and I have a new matrix of the same size. What does that mean for this function T1 and T2? You were thinking it correctly, but the correct word for what you're trying to say is composition. So you do go through the function T1, T2 first. Then what is the symbol for composition? Little circle there, right? And T2. So if I give you a vector, you go through T2 first, right? Then you have another 2 by 2 size 2 vector, right? Then you go through T1. So you start with a one vector, go through T2, and then with that output go through T1. That's a composition. So what is the result? The result is simply multiplying by your new matrix Mn going through there, right? So that's the meaning of matrix multiplication. But that's not what we're concerned in here, only the scalar multiplication. All right. So here's maybe a little challenge there. So you know the R3, right? The side by 3 column vector. I'd like to put this one into space of function. Right? I want to look at this as a space of functions. Right. Let me explain it this way. I have a function f of xy, f of x, that is given by a polynomial x, where p is coming from, let's say, polynomial of the real coefficients. Right. Then we view this f as a function of real number to the real number. We talked about that already, right? Okay. But I want you to go ahead and change this domain to something else. which is a set of 3 elements, which is 0 and pi and e. Maybe e first. It's weird. E is at 2.71 and pi is at 3.1. So domain only has 3 elements, right? And it goes to real number. It's given by f of x given by some polynomial px. Okay? So let me go and change it so that I can finish in a short time. So simply 1, 2, 0, 1, 2. So when you look at, for example, so I hope this described to you as vector space. Vector space W, I'm going to like to say f going from 0, 1, 2 to R, such that this f of x is given by some sort of polynomial. Does that make sense? Okay. So here, if f of x is x times x minus 1 times x minus 2 times x, and if the g of x is given by x minus 1 times x minus 2 times the square plus x, you're looking at the 2 different polynomials, right? One has degree 3, the other one has degree 6. Degree 4 actually, because I squared that part, right? These are 2 different, polynomials, right? But as a function on these 3 points, do you believe this is the same function? Because f of 0 is, because of that 0, it's a 0, right? You see what I'm doing? G of 0 is, because of that 0, that's exactly the same. So because this guy is the same, and this part acts trivially on the domain, these 2 functions will be exactly the same. You believe that? So although these 2 polynomials are different, we say f and g as functions are the same. Right? So this function here, this polynomial, this function is all about where 0 is going, where 1 is going, where 2 is going. This function structure is all about sending 0 and 1 and 2 to some sort of number, a, b, c, right? Therefore, if I'm looking at 5 and 6 and 7 inside size 3 column vector, that is corresponding to the function that f of 0 go to 5 and f of 6 go to f of 1 go to 6, f of 7, f of 2 goes to 7. Each of the column vector in size 3 can be viewed as a function that is sending 0 to that number, 1 to that number, and 2 to that number. Right? So even R3 can be viewed as a space of functions. R3 wasn't a space of functions, but you can be viewed as a space of functions. So what is advanced linear algebra is about? Looking at the space of functions. Not defined. It's not defined. Our domain only cares about 0, 1, 2, right? So if that's your definition of the function, that's how it goes. So developing, looking at the space of function in terms of column vectors going back and forth is basically what this advanced linear algebra is about. Right? So let me summarize it here and let you go. Space of functions back and forth with this finite dimensional vector space. How do you view that? And eventually we deal with infinite dimensional vector space. Therefore, we can't do this anymore. And then you really have to rely on abstract theory.